Hello, I'm Jake Massimo, and today I will be talking about joint work with Kenny Patterson on a Performant Misuse-Resistant API for Primality testing. This work uses Primality testing as a case study for the design, implementation and use of secure APIs. So today I will give a short overview of the work, starting with some motivation and background, in which we shall briefly discuss Primality testing and API design. Then we'll move on to contributions and results, in which we shall discuss how we might go about the design and implementation of a secure API. And then we'll end with some brief conclusions and recommendations and reflect on some lessons learned. Okay, so let's start with some motivation and background. So why are we looking at primality testing? Well, primality tests are widely implemented across cryptographic libraries and mathematical software. Work by Albrecht et al. In 2018 performed a study of the implementation landscape of these libraries and found that 11 out of 16 would classify composite numbers as prime with a rate higher than documented. In 8 out of 11 of these cases, the authors actually went on to achieve incorrect prime classifications 100% of the time. And these were for some big names as well, like Apple Core Crypto, Common Crypto, GNU GMP, Wolf SSL, just to name a few. So what was the cause of this discrepancy between the test's documented performance and the actual performance? Well, there are a few contributing factors. Many of the test studies neglect to consider the adversarial setting and used bounds of accuracy based on the incorrect assumption that all numbers tested would be random. We call this a mistranslation from theory to practice. Another reason for this discrepancy is that the documentation was either misleading or that simply the API calls was insecure by default. Now this would usually go unnoticed, but the adversarial setting really took advantage of this. So in this work, we look at how we can mitigate these issues to make primality testing robust in the face of crypto unaware developers, and hope that the lessons learned here will raise awareness of this issue more generally. So I'm now going to start with a small example in which we'll look at OpenSSL and see their primality test API and some of its documentation. So OpenSSL is a widely used open source cryptographic library in TLS implementation. It's the default encryption engine for Apache and Nginx web servers, which hosts 62% of websites online today. But it provided, or at least in May 2009 prior to this work, it did provide a complex, poorly documented and insecure by default API. So let's look at it in a little bit more detail here. So here we lay out the API. This BN is prime fast test X, and we'll look at some of the important arguments. So first W, the big number that we want to test, and then we look at checks. Now this is how many rounds of testing is performed. So if checks is set to the default value, which is BN prime checks, then this sets the rounds such that the false positive rate is at most 2 to the negative 80. One other important argument we'll look at is the do trial divisions flag, which sets whether or not trial division is performed. Now let's look a little bit closer at this checks parameter, as this is really what controls the accuracy of the test. So when checks is set to default, this is the table, or the lookup table that is used to find out how many rounds of Miller-Rabin to perform. Now looking at the description, it seems like the perfect tool for the job. You could imagine a developer who needed to perform a primality test asking themselves, what shall I put for the value of checks? And seeing this lookup table here and saying that it produces an error rate of less than 2 to the negative 80 and thinking, great, I'll go with that. But of course, the caveat to this bound is that this is only for random input. Now here's a very important distinction. These bounds give error rates less than 2 to the negative 80 on random numbers tested, but for adversarial input, we need to consider the worst case error estimates, and these are much, much bigger. For example, for a 1300 bit or bigger number, this function would just do 2 rounds of testing, and this would declare an adversarial composite as prime just 1 in 16 times. Now perhaps this sounds to you like a mistake you wouldn't make, that a developer would surely know the setting the test is called within, random or possibly malicious. However, we see that even OpenSSL misuse this test within their own library. So many cryptographic libraries include validation functions that check that public key parameter sets appear good for use. An example of such a check is OpenSSL's DH check. This is used to confirm that DH parameters are valid. The test, among other things, performs a primality test on both P, the prime used in Diffie-Hellman, and Q, the order of the subgroup generated. However, when calling the primality test on P and Q, OpenSSL calls the test with checks argument set to default, so it's determined by the function that we previously described. Now this clearly is not the use case of testing randomly generated numbers, as any parameter set provided by another party could be possibly maliciously generated and could undermine the security of the connection. So where does this work fit into the field? Well, we see this firstly as a step in mitigating the issues raised by previous work on attacking primality testing in cryptographic applications. So this is the likes of Prime and Prejudice in 2018 and Safety in Numbers, a follow-up in 2019 by Galbraith et al. But this work also more broadly fits into recent efforts to promote usable security and safe APIs. We see this from work from Green et al. And Akar et al. In 2016. Now, similar work was also seen during Rogoway's publication on nonce-based symmetric encryption. We also see some cryptographic libraries implementing secure and misuse-resistant APIs as a core tenet. Cryptlib and NaCl or SALT are a very good example of this. So now we'll move on to some of the contributions and results of this work and look at the design and implementation of a better API. So in this work we ask, is it possible to design a robust, performant primality test whose API has a single input n, just the number being tested? But of course there is a balance that comes with this level of simplicity. The more misuse-resistant this API becomes, the less accessible the API is to developers, and the fewer options or these fine-tuned different use cases that it can provide. For example, there would be no longer the option to add or remove trial division. In this case, we must also use the pessimistic settings. We must assume that the worst case, that the inputs are malicious. We saw in the current OpenSSL that they just assume the random case, and this can potentially lead to some disastrous results. But of course, with more rounds of testing, more assurance, then surely there'll become an impact on the performance of the test. So in designing this new API, we looked at alternative methods for the underlying primality test. The first test we looked at was the Bailey PSW test. Now this test is fast, it's deterministic, but it has no proven security guarantees. Now there are no known pseudoprimes to this test, but in fact there is a small monetary reward for finding one, yet none have been found. So there is a heuristic argument by Performant that says that infinitely many of these pseudoprimes do exist, and if there were no counterexamples, then this test will be cubic in time, dramatically improving on the much famous AKS test. The other option is to simply perform more rounds of Miller-Rabin. Now we know the error rate of Miller-Rabin very well, and we know that 64 rounds will have a worst case error estimate of 2 to the negative 128 on composite input and 0 on prime. But this test does consume randomness, and when the input is prime, then all 64 rounds of the test will have to complete, which can mean it can take a little bit longer. Now we can compare both of these tests to what OpenSSL is currently doing. This is what we call the Miller-Rabin average case. Now this is a sort of fast and loose test that works well on random input. Now there's one more step we need to consider here, and this is any preliminary testing that is done before the primality test. Now often primality tests use some sort of trial division with some small dividers to speed up performance. OpenSSL offers this with this do trial division flag, and this does trial division with the first 2047 odd primes. So as part of this work, we want to more formally describe the effect of trial division on the performance of the test as a whole. Now here we plot the number of primes used in this trial division stage along the bottom versus the portion of candidates removed along the side. We can see that from this curve that the first few primes make a huge improvements to the number of candidates removed, and at around the 128 mark we remove 83% of composite candidates. However, we can see diminishing returns pretty quickly here, and if we look at how many primes OpenSSL is trial dividing by, we can see this is a huge overkill, and really we should scale this back to something a little bit more sensible. So we now summarise the recommendations we made to OpenSSL based on the analysis of this work. This table shows the various bit sizes, the number being tested, and how many rounds of trial division we advise, which is optimised to balance both the most candidates removed by the trial division and the least amount of time taken. We then show the error bound for the current OpenSSL implementation, both on random and adversarial input, and compare this to the error bound that on the test we introduce, MR64, which has the same error bound for any input of 2 to the negative 128. We then provide the overhead incurred when testing on random input. So this is shown for 512-bit and 1024-bit that we actually improve on the running time by 35% and 17% respectively. However, for larger bit size, Miller-Rabin can take a little bit more time, so it actually causes a slowdown, and we see a 14% and 25% slowdown on 2048, 3072-bit input respectively. But this is a small price to pay for a vastly improved error rates at these higher security levels. So to summarise, in this work we provide an overhaul of the primality testing API in OpenSSL. The API will now provide strong security guarantees across all use cases, the simplest possible API, and a more efficient way to perform trial division. OpenSSL responded to our recommendations well, and have included the APIs we introduced into OpenSSL 3.0, signifying the biggest change to the Primality testing code for OpenSSL in nearly 20 years. So now we'll just finish off with some short conclusions and recommendations to reflect on outcomes and lessons learned. So for crypto library developers, we recommend that you maintain a conscious effort to design simple, performant, misuse-resistant APIs for cryptography. Balance code simplicity, performance, and security guarantees across all use cases. But also think about how the API is likely to be used, either elsewhere in the library or by developers relying on your library. Do not rely on developers to read code comments concerning your test performance. Try to simplify the API as much as possible, and as we see in this work, this might be done without adversely impacting the performance. So, thank you for listening. You can check the papers out here on these links or contact myself or Kenny.